Hi everyone. This is going to be a somewhat scuffed pre-lab video. I apologize. I'm not at my desk with a second monitor just because I'm not feeling quite up to sitting up like a normal human. I'm having some difficulties right now. So just excuse the scuff. And let's just talk about multiple regression. So, today, for this week's lab, we're going to continue working on regression. Today we're going to look at the rest of the assumptions. So we only really looked at influential observations in last week's lab. Now we're going to look at all of the rest of those assumptions. And we're also going to take a look at different entry methods for the regression. So there's a lot to cover for today, so let's get to it. So as you can see, our data set today is about Christmas, because we like to try to make stats fun here. If you couldn't tell by the zombies and vampires and now elves, we want to at least pretend like it's fun. So our data set gives us essentially a bunch of information about the elves, and we want to try to figure out if, using this information that we have about the elves, we can figure out how many toys they are going to produce. So are we able to predict the number of toys that they produce using these predictor variables? So, first things first, as always, we need to check our assumptions. There's a number of assumptions in MRA. Like I said, we only really covered the absence of outliers and influential observations last time. But that is definitely the biggest and most complicated one to check. So, the first assumption is sample size. For regression, you need to, you ideally want to have about 15 cases per predictor variable. So here, if I scroll back up, you can see we have 9 predictor variables, or 8 if you exclude the employee number. And so 8 times 15 is 120. I think I did that math right. And so that means that in order to meet the sample size assumption, the rule of thumb would tell us that we need at least 120 cases or participants in order to have a large enough sample size to be able to run this. Now, I believe that our data set that we'll be working with has well over that, like 400 or something, 500. It's quite a big data set. So for this, we don't really need to worry about sample size. Next is absence of outliers and influential observations, which we'll have to run through the same way we did last time, though I'll go through it a bit quicker. Then there's a couple new ones. So absence of multicollinearity and singularity. So I'm sure you already learned this in class, but this is essentially, we don't want our variables to be too closely correlated, right? So it makes it really hard for the regression to tell, what is predicting what when things are basically the same. So here, there will be collinearity diagnostics and statistics that we can use, but the rule of thumb would be we don't want our predictor variables to be correlated higher than 0.9. If it's over 0.9 of a correlation between predictor variables, then it's probably a problem. Now, the next thing that we have is normality of errors. So you'll notice if you look at all of these things in here, there's no normality. The data itself doesn't have to be normal. So that actually is one of the strong points of a regression, is you can do it with non-normal data. But instead, we need the normality of errors. Essentially what this is saying is we don't want this trend line to be worse for certain values than for others. So if we were to draw out the line, and say 0 toys made up to like 10 toys made, something like that, maybe all of the points for 0 toys made are actually like right on that line or super close, whereas all of the points at 10 vary wildly. This essentially means that the trend line that we make using the regression fits better at one point, at like one part of our model than others. And that's a problem, right? It means that the error is not accounted for in the way that we want it to be. And there's something probably wrong with the model. And we'll talk in a little bit how to look at that. Next up is linearity. Now I believe we looked at this very briefly last week, but essentially the idea is regression gives you a linear option, right? It's not going to compute a quadratic function for you. It's only a line. So if the relationship between these variables isn't a line, it's not going to be able to do it. So there's another, we'll go over how to look for linearity as well. Homoscedasticity of errors is another fun mouthful. And here, this is essentially saying, it kind of goes back to that normality of errors. It's slightly different, but essentially we want all of the error to kind of look random, right? Because it should be random. And if it isn't, then we have a problem. Finally, independence of errors. So this assumption is always going to be there basically, and we can't test for it. In independence of errors, you have to do based on study design. Here, we're just going to assume that whatever they use to test for this gives us independence of errors, even if probably it doesn't. And then the final assumption here is that all relevant variables are in the model. We're never going to have this be fully met, right? Because if we think about the world, everything is connected in some way. But essentially, we don't want... We want to have all of the important things in there. If there's, we know that the color of leaves is based, not just on the tree, but also on what season it is. And like, if you don't have the season in there, well, that's probably going to be a problem if it isn't equal across all of them. So yeah, that's just essentially, do you have everything that you need in there? You'll never really have everything, but you want to have most things. Okay, so here there's instructions for running this, and I want you to pause the video now to go through all of this and come back and we will interpret that output. Okay, I hope you listened to me and paused. I always feel silly telling people to do things, but I think it's important that you run through it yourself. Okay, so first thing we have here is just some descriptive statistics. So the mean, standard deviations, and N. We don't need to look at this right now. It's not super important. Next up is the correlation table. And if you remember, for this, we essentially are looking for to ensure that there isn't any multicollinearity. So if we look at all these, it doesn't appear that there's any with a correlation above 0.9. For toys, since toys is our outcome variable, we want everything to be fairly well correlated with toys. You'd assume that it would be correlated for it to be in the model, though some things won't be as strongly and might still be useful to look at. So this is one of the things for checking for multicollinearity. It looks fine. Don't worry about this. We'll talk about it later. And don't worry about most of this because it is part of the interpretation, which we're not doing yet. What we do want from this table is the Durbin-Watson. Now, the Durbin-Watson is something that we use for testing the independence of errors. So, like I said, independence of errors is typically based on the study design, but the Durbin-Watson can kind of help us understand if the error, the amount of error in the model is correlated with the predictor variables in the model. So for the Durbin-Watson, we just want the value to be between 1.5 and 2.5. So essentially we want it around 2. Here we see that it's far below that, and that's probably indicative of other problems. Now if we look down, there's the general ANOVA table. We don't want to look at that yet. And this coefficients table. For this, since again we're not interpreting it yet, what we want to know is this collinearity diagnostics. Tolerance and VIF should always tell you the same thing. They're inversely related, so they should never really tell you separate things. Sorry, every time you see the thing get small, it's because I'm like looking at all of my windows. So there's for tolerance, we want it to be above 0.1, and we want VIF to be below 10. A normal, when they're normal, they'll both be around 1. So as we see, nothing is below 0.1, nothing is above 10. We're fine. These all look good, which tells us the same thing as the correlations. Now, next, it gives us case-wise, so we don't need to worry about this collinearity diagnostics because we aren't having any problems with collinearity. But if we look at this case-wise diagnostics, this is actually very helpful for us because it is essentially telling us, ooh, here are some cases that look like they could be problems. So how it's doing this is essentially it has the number of toys, it has the predicted value for the number of toys, I believe, and then what the residual is. So how far away the actual value is from the line, and then it standardizes it. So essentially, this is using a 2.5 cutoff, which, as we discussed in last lab, since there's about 500 cases here, 2.5 is a little bit conservative. 3 would be a more liberal cutoff that I would probably be more likely to use. So worthwhile to, but these are ones that have kind of been flagged as possible problems. Interestingly, if we look at case number 1, toys, it says that the value is -43. And that tells me right away that this is probably an inputting error. Because it does not make sense for someone to have negative toys. So that is a case that is going to have to be removed, most likely. Then we have the statistics about the residuals. So we don't need to really look at these too much. These are essentially those values that we talked about last time for finding influential observations and outliers. These are all the different ones, and it just is giving you essentially descriptives for those. I'm not going to go over finding outliers for this. That's something that I'd like you to do on your own. And the rest of these assumptions really should be getting tested following looking at removing any outliers / influential observations, which, as I noted, influential observations are much more important. Okay. So the next thing here that we have is the some charts. So this first one is, we can see it's making a very nice bell curve, and this is regression standardized residuals. So this is essentially the error term, all the error. Residuals is another way of, essentially a residual is just a measurement of error. And so this is saying, okay, how is that error laid out? And here we're seeing, well, this is a bell. Like, it fits pretty well into this bell shape. And so if we go back and remember those assumptions, normality of errors, well, that was one of them, and this is something that is telling us, okay, this fits a normal curve pretty well. If we look at it another way, we can look at the PP plots and the QQ plots for the residual. And here, again, we're looking at how closely does it follow that line. There's a little bit of a wave here in the middle, but overall nothing huge. This looks like it follows that line pretty well. Then we can look at the scatter plot. Now this scatter plot is actually one of the most useful things that you will get for determining the assumptions. Now, what do I mean by that? Well, let us go back to this document. So, here we have some diagrams to help you understand some of these things. So, as I already said, multicollinearity, some things are too closely correlated, versus no multicollinearity, things are better. Now, this plot that I was just talking about, that's what we actually use to determine if there's normality of errors, and if there's and that there's homoscedasticity of errors. So here we have a couple different plots, and I want you to kind of just look at them. So there's the predicted value along the bottom, and the residuals along the side. So essentially what this is telling us is, do the residuals change based on the predicted values? Or essentially, like I was talking about before, is the model better at one end than it is at the other? Now what we really want to see is this nice uniform variance around essentially 0. So there's same above and below 0. What we could instead see is what is on this top right graph here, where it looks like, for predicted, along the predicted y, it's still pretty standard, like it looks approximately even all across, but there's a lot more variation along this bottom. So cases where the actual y is less than the predicted y. And essentially what this is telling us is that the model isn't working quite as well for certain cases in a way that isn't distributed normally. So essentially, it's not normal. And that's what it's telling us, that this is non-normality of errors. On this bottom left, we have another situation. So here, we're having a case where, as predicted y is increasing, the error is getting much wider. So we have this fan shape. It's fanning out. So the model is very good for these smaller values of the predicted y, but gets pretty bad after. When you see something like this, this suggests that, well, this might not be linear, for one thing, but it also, it looks like there might be more than one effect in here, because the model works pretty well, but only up to a point. So essentially that's what we're looking for, these types of differences, when we're looking at this table. So if I bring us back to that, remember what we're looking for is an even distribution around this 0 line. So a similar variation above and below. You can tell that we have a bit more below than above, and I'm saying that mostly because, well, the graph has decided that we need to go to -4, where we aren't going up to +4, and my guess is that this is the problem case that we came across, that -43. So it looks like there's a couple of cases, and what you end up finding after you take out the outliers is like maybe things will look a bit different. Maybe they'll look better. Maybe they'll look worse. So when you look at this, remember you want to see, is there this symmetry above and below the 0 line? And is the relationship above and below the 0 line the same across all of the values? So this looks pretty good. It's a nice circle. We're not getting that fanning out. It's maybe going a little below, but not too much. A lot of students hate looking at these assumptions because it's very subjective. But we'll talk about it more in lab, probably. Okay. So, going back to the lab document, we have this table in here for you. It's a little blurry, but I love it. I think that it's really helpful. And if I were you, I would refer back to it fairly often. Obviously, like, this isn't something that you should cite, but it's something that like you can use as kind of that guideline. And so it tells you, okay, here are all of the assumptions, and what do I do with the assumptions, and even whether regression is robust to these assumptions. So it's not robust to sample size, but it can be robust to outliers, right? Like I said, it can be robust to absence of outliers, but not for the influential observations. So yeah, this can kind of help you figure out what are those cutoffs, what should they be, and how your data is looking. Now, I'm not going to go through this with you now. We can talk about it more in lab on Monday. But I'd like you to fill out this table. So put in the test, like what you used and the value that you got, or what you saw, and then how would you interpret that? I would suggest that you do the absence of outliers and influential observations first, and then evaluate the rest, because you'll likely have to take out cases, and then you'll have more difficulty. You'd have to redo some of the other ones since you've taken cases out. Okay. So, once you've done that, let's interpret. So, I'm going to ask you to pause the video now and do those assumptions take out those outliers or influential observations and come back and let's see what the regression looks like together. So we just used as the GAs, we just used a simple thing to cut off cases that were outside of our outliers, like that were considered outliers or influential observations, and I'll go over what we did for that in lab. So I'm just going to now look at this model and interpret it as if all of the assumptions are met. And we'll talk about the assumptions once we get to lab. So, if you haven't looked at a regression before, it can be a little confusing because there's a lot of different values. The first thing you want to look at is in this model summary table, you want to look at the R-square and the adjusted R-square. R itself isn't as important. It's really hard to interpret on its own, but R-square is essentially proportionate to the variance that is accounted for. So how I would interpret this is I would say the model was able to account for 24% of the variance in a number of toys made. Adjusted R-square is sometimes actually a better use compared to R-square. It essentially just adjusts for natural coincidence, essentially. So adjusted R-square is always going to be a bit smaller than R-square, and that's just because it's adjusting for the fact that we're throwing a lot of variables in there, and some things might explain some variance completely by coincidence, by random. Okay, now we don't need to look at the standard error, at least right now. It's not really that important to us. That's essentially just saying, how confident are we? We don't need the R-squared change because this was all entered in one step, which we'll get to. And you'll see that the F change, DF1, DF2, and F significance of the F change, that's actually all the same as we get in the next table down, the ANOVA table. And this next table down essentially is just telling us the significance of the model. Sometimes this will be different, these change statistics. Now, the model summary, that will give you the results for each step, which is something that we'll talk about, whereas the ANOVA table just gives you the results for the overall model. All of that will make more sense once we actually get to ones with multiple steps. Okay. Now, the next thing to look at is this table marked coefficients. This table is essentially telling us, okay, so we saw above the model is significant, it's explaining a significant amount of the variance. Why? Well, if we look here, we can see that there's a number of coefficients or predictor variables that are significant. And I can tell that by looking at this significance column, the fifth column here. So as always, ignore the constant, because for most of the psych that you will do, it does not matter. So we can see that these like all but dexterity and deer, everything else is actually significant. It's explaining a significant amount of variance. And I'm telling that, again, simply by this significance column. When you're reporting this, you want to report the t and the significance. Now, let's go back and look at these first three columns here. So there's the unstandardized B, the standard error, and then there's the standardized B, which we call beta. The difference between these columns is simply that it's been standardized. So it took the original values and divided it by the standard deviation. So they tell you the same things, but in different units, essentially. So these first two columns, the unstandardized coefficients, if I look at tenure, for example, how I would interpret this first column would be to say, for every 1 unit increase in tenure, which is likely 1 year, so every 1 year increase in tenure, the number of toys made per day increases by 0.075. So, put another way, this first B column tells us the change in the outcome variable per 1 unit change in the predictor. Alternatively, we can look at the beta weight. Now, the beta weight is telling us what is the change in the outcome variable for every standard deviation change in the predictor. So how I would interpret the beta weight here would be to say, for every 1 standard deviation increase in tenure, there's a 0.31 standard deviation increase in number of toys made. Which one you use really depends on the situation. Does it make more sense to use actual units, or does it make more sense to use standard deviations? So here, it might make more sense to use just units, right? A unit has meaning. Tenure, tenure is measured by years. Toys is measured by physical number of toys. But when we do a lot of things in psych, depression, what does 1 unit increase in depression really mean compared to, a standard deviation increase in depression symptomology? That's something that is more understandable. So which column you use simply depends on what you're using. It's really just which one is kind of easier to interpret. Moving over in this table, we have our 95% confidence intervals. So this is for B, not for beta. If you're using B, you could report this as part of your significance statement, but it's not not that important, as long as you're already reporting the standard error. You can figure out what the 95% confidence intervals are if given B and standard error. But the final, and probably one of the most useful parts of this table, is actually this correlations section. So here we have 3 different types of correlations: the zero order, the partial, and the part. Zero order correlations are what you would see normally. So it's just comparing 2 things together. How much variance do they share? Partial, on the other hand, is saying, okay, well, how much of this variance that they're sharing is unique? Just like is only accounted for by the 2 of them and not by other ones. So if we take out all of the variance that is being accounted for otherwise in the model, how much is just this thing accounting for? And then finally there's the part correlation, which is if we leave in all of the variance but only look at just the unique variance that this is giving to us, then how much is it predicting? So essentially, this can be a really, really good way to figure out what predictors are most important to the model. More than looking at the B or the beta, we really want to look at these part and partial correlations. The higher the correlations here, the more variance that the more variance that the predictor is able to explain in the outcome variable. Now, interestingly, essentially, if we wanted to, we could square the correlation, this partial or part correlation, and that would, I think, part actually. We could square the part correlation, and that would tell us the amount of variance in toys that can be explained by tenure. Can be uniquely explained by tenure. That uniquely aspect is actually really important when you start looking at the partial and the part correlations. If this is confusing to you, do not worry. It took me so long to really understand the difference between these types of correlations. And we'll talk about it more in lab, and I'll probably draw annoying pictures because I just like drawing pictures sometimes. Yeah, so that's kind of how you interpret this table. Going back to the document, saying how much variance has our overall model accounted for, which I already said, and what predictors are significant, which I also kind of went over. So fill that out, and then come back. Okay. Now, the last aspect of this lab, and sorry, it's getting a little long here, I know. The last part is entry methods. So what are the different entry methods? Now, this can be confusing sometimes because, typically we just throw everything in there and see how it goes. But when we think about a regression, our predictor variables, those are all correlated, right? So the amount of tenure someone has probably is correlated with the amount of spirit that someone has. And so if the variance that's explained, like that tenure and spirit have in common, is used to explain toys, well, does that explanation come from tenure, or does it come from spirit? Right? It can be hard to kind of piece out causality. Regression, you can never really do causality with regression, but you can do it a bit better than just putting everything in at once and go. So let's look at what some of the different options are. The first one is a hierarchical regression. Essentially, here, what we're doing is we're saying, okay, I think that, in this case, tenure and spirit are primary. They're the most important. I want to kind of level out the amount of variance that they're bringing into the model. And then I want to see if other things add anything useful on top of that. So, in this case, games and candy. Do games and candy help explain the number of toys made above and beyond what we already know based on tenure and spirit? So, let's run this. Let's run this and look at it. So, you can just copy-paste this syntax into SPSS, and let's go. Okay, so here's our syntax now. Again, I'm going to just ignore a lot of it. Here we see, oh, there's actually something in this variables entered/removed table. We have two models, and that's because we entered things in two steps. So first, spirit and tenure were added, and then games and candy were added. Now, this model summary table is useful. It isn't just telling us the exact same thing as the ANOVA, although they still tell us similar things. Now, it's giving us this R-square change and F change. This is telling us what additional information, how much more variance we can explain in the model based on adding in games and candy. So for this, how I would interpret it, so if I'm looking just at this model 2 line, I might say that games and candy accounted for 5.5% of the variance in toys, above and beyond what was already explained by tenure and spirit. So again, it's that above and beyond, or uniquely. And we know that that is a significant amount of variance because of the significance of the F change. If we just want to know if the model overall, the model with all four things, is significant, then we instead would look at this ANOVA table at model 2. So here we have everything combined. Okay, now we can look at this coefficients table. So things will likely be fairly similar for tenure and spirit, but yeah, you can notice that there's actually a slight change in spirit here in the beta weight and the B weight too, you can see that the values change slightly. And if we go over to the correlations that we got, well, the zero order are the same, because remember, that's because nothing else is put in there for the zero order. But the partial and part, the correlations that we got for Model 1 are slightly different than we got for Model 2. And that's okay, because that's why we're putting it in 2 steps. Remember, partial and part, those are ways of kind of, well, partialing out other sorts of variance. And so this is how we can say, okay, this is the amount of unique variance added to the model. Okay, so that's just some rambling. The important thing to note here is, again, everything was entered in 2 steps, so it's hierarchical because essentially we're saying we want you to put in these variables and then other ones. So there's a hierarchy of when you put variables in. This can also be called stepwise, I think, unless that's another. I think it can be called stepwise. And then we want to look at these change statistics because that tells us, was it useful? Did the variables added actually add meaning to the model? Okay. So you can fill out this table based on what we just talked about. And this is how to put it into SPSS. Oh no, stepwise is something different. I always get confused. Okay. So, next up is these default entry methods that SPSS has. Typically, you don't really want to use these. Essentially what they're doing is they're using an algorithm to try and determine the proper number of, like the most ideal number of predictors to put in. So they all work in slightly different ways. Forward will keep adding variables, going from the highest amount of variance decreasing until there isn't a significant difference anymore, and then stop. Backwards will start with everything in the model and then remove things that aren't significant until there's a model where only things that are significant are in it. And stepwise uses a combination of the two. You can just modify the syntax here. If you see the final line of the syntax, method equals forward, just change that to stepwise or backwards, and you can run all 3 of them. So using what I've already talked about for how to interpret the significance of each step, fill out these tables. And that is everything for this week's lab. Sorry that this is an hour-long recording because I'm incapable of keeping things short and sweet, but I hope that it was helpful. We will go over all of this in lab on Monday. I think I went over it in more detail than I was originally planning on. But hopefully that's good, and we can go over it again. I'll definitely, we'll talk about what you wrote for each of these tables, and answer any questions you have, and definitely talk a bit more about how to interpret those partial and semi-partial correlations. Good luck with this lab, good luck with everything right now, and see you all on Monday.